Okay, hello everyone. I'd like to start by expressing empathy and condolences to the Israelis, Palestinians among you, those who have friends and family from that area. I personally am one such person, and I know it's not easy these days. So if you need any support, accommodation, let us know. I know that I do. I know that I was not able even to prepare this one meager lecture that I was supposed to finally give. So I'll do what I can. I'll tell you a little bit about the AEP and mismatched decoding or mismatched compression, and then I'll hand it back to the more capable parts of our teaching staff. So I want to tell you a little bit about the AEP. Okay, that's the asymptotic equipartition property, and how it relates to compression, lossless compression, and the fundamental limits on compression. So, and we're going to do, those of you, and hopefully most of you, who will take 276 in the next quarter, we're going to do this stuff very kind of rigorously, mathematically, concretely. So here, I'm allowing myself to just sort of try and give you the gist, the essence, qualitatively, what this is about. I'm going to spare you the epsilons and the deltas. And in fact, I'm going to do this through just one example, which if you sort of understand the essence of this example, then you really understand the AEP. So let's consider, yes? Okay, bigger, and I can use this, the whole thing? Okay, so up to here? Okay, great, but bigger than this? Okay, so let's consider data, like xn, right? We use this notation for the n tuple, okay? x1, x2, up to xn. So this is an n tuple of data that you want to compress, you want to represent it with bits. And let's suppose that this, again, the simplest non-trivial example is when these guys are generated IID according to some generic random variable x, which let's assume for this example is binary, also binary, and with some, oops, sorry, I forgot the bigger, with some Bernoulli parameter p. Okay, so each one of these components is just generated IID, like fair coin flip. The probability of a 1 for each of these is p. Okay, so that's your source of data that you want to compress. So what do we know then about this n tuple that you'll need to represent? Well, we know that with high probability, right, and this is from the law of large numbers, so this means with high probability, with all likelihood, this n tuple, xn, is going to have a few properties. So let's see. It's going to have, well, number one, how many, like approximately, so again, these guys are IID, Bernoulli P. So approximately, how many ones am I going to see here? Like, I'm going to see zeros and ones. Approximately, what fraction of these components is going to be ones? P. Right. That's the law of large numbers applied to this case. So, right, approximately, we're going to see n times p ones. Everybody okay with this? And similarly, how many, approximately, right, like, then how many zeros are we going to see here? Right, the remaining places, which is fraction 1 minus p of the places. So approximately n times 1 minus p of the components are going to be zeros. Right? And so number 3, for this sequence that was realized by flipping these coins, I'm going to look at this sequence and ask, oh, in retrospect, what was its probability? So I'm going to ask, and I'm sorry for a slight abuse, I mean, this is P that represents the Bernoulli parameter, but this is like bigger P that represents the probability of this realized sequence. Okay, so I'm going to look at this realized sequence, some zeros, some ones, and I'm going to ask, hey, you know, what's the probability of seeing such a sequence? Okay, so that's going to be, right, approximately, right, in fact, before approximately, let's ask ourselves exactly what is this going to be, right? So what's the probability of seeing some particular sequence that has like 0 here, 0, 1, 1, 0, 1, 1, 0. What's the probability of seeing exactly that sequence? What was the attempt?
1 over 2 to the n.
Oh, 1 over 2 to the n. 1 over 2. Okay, note that would have been true if p were a half, right? Then all sequences are equally likely. Each has a probability of 1 over 2 to the n. Okay, but now these sequences come with a bias, with a probability of a 1 being p, right? So what's the probability of seeing a particular sequence, 0, 0, 1, 1, 0, 0, 1, 1, if the way that I generated these sequences was IID Bernoulli P?
It depends on the number of ones.
Right? How?
P to the power of k multiplied by 1 minus p to the power of n minus.
Exactly. So it's going to be P. So, you know, this is small p. So it's going to be, in fact, exactly small p, this small p that governs the bias in these coin flips, to the power, let's just write in words, right? Number of ones in this sequence, in xn, right? Times 1 minus p to the power number of zeros in xn, right? Every 1 here gives me a factor of p. Every 0 gives me a factor of 1 minus p. Okay? And so approximately, right, by these two properties, this is going to be then what? P, right? This small p to the power number of ones, right, with high probability is going to be about np. Right, times 1 minus p to the power of zeros, which with high probability is going to be n times 1 minus p. Right? So That's equal to what? It's equal to, well, I can always write this as 2 to the power log base 2 of the same thing, right? So it's 2 to the power log base 2. When I don't write the base, it's just base 2. 2 to the power log base 2 of the same thing, right? That's p n times p times 1 minus p n times 1 minus p. Right? Which is what? 2 to the power n log of, or I have here the p that comes here, p times log of, in fact, let me do this, 2 to the minus, let me pull out a minus here. So I have p times minus log of p, or in other words, log of 1 over p, plus 1 minus p log of 1 over 1 minus p. Does this look familiar? What is this in terms of a quantity that you recently encountered and defined? Right. This is exactly the entropy of these components, of this random variable x that describes them, right? It's p, right? The entropy. Maybe we should remind ourselves, right? In general, the entropy of a random variable x, right, was defined as the sum over all the possible values, small x, that this random variable can take. Its probability, the probability of the small x, log 1 over the probability. In the case of Bernoulli p, something that has 2 possible values, 1 with probability p, so that's the p log 1 over p, and then the other value, the other possible value 0 that has probability 1 minus p, so that's the other value, 1 minus p log 1 over 1 minus p. Okay, so this is nothing but the entropy of the source, which is generating your data. So, okay, so with high probability, with all likelihood, the sequence that you're going to get is going to have, when you look at it, you're going to ask, oh, what's the probability in retrospect that's the sequence that I got? Well, its probability is about 2 to the minus n times the entropy. Everybody okay with this so far? And so now let's ask ourselves, how many sequences with this property, with this, let's say, with this property, okay, with this. Okay, so how many sequences have the property, right? So this is these are binary sequences, right? Overall we have 2 to the n possible sequences, but how many of them have this property that their probability is about 2 to the minus n h? Is there a question? right? So let's think about it. Collectively, right? All the sequences with this property, so collectively, their probability is essentially 1, right? Because I said, we talked about how with high probability, right, the law of large numbers tells us that with high probability, with all likelihood, in other words, with probability essentially 1, right, the sequence that we're going to get is going to have this property. Okay? So collectively, all the sequences with this property have probability about 1. Okay? And each of them, but by definition of this property, each of these has this probability. Has probability approximately 2 to the minus n h. So how many such sequences are there, approximately? Right? We've got a collection of sequences, I'm asking about a collection of possible sequences that could be realized, right? Collectively, all the sequences in this collection collectively have probability about 1, and each of them individually has essentially the same probability, about 2 to the minus nh, right? So how many sequences are there? Must there be in this set that I'm asking about? Right? They each have essentially the same probability, the same small probability, and collectively the sum of all their probabilities is about 1.
2 to the power of nh.
Right. Essentially 1 over their individual probabilities. Right? They each have essentially the same small probability. Let's say epsilon. Right? I'm asking about the size of a set, each component of which has the same small probability, epsilon, and the sum of all the probabilities of the elements of this set is about 1. Right? So the size of the set, so the number of sequences is about 1 over that epsilon. Okay? It's essentially like a uniform distribution on this set that has most of the probability about 1. Okay, so the conclusion is that there are approximately 2 to the n, like basically 1 over this epsilon. So about 2 to the n h such sequences. Okay, and they are called, we call them, they are referred to as typical sequences. Okay, so it slightly depends. We won't get into it here. Again, 276, we'll say more. Sometimes typical sequences, we require all these 3 properties, or we require just this, but in any case, it's essentially the same thing. With high probability, because of the law of large numbers, we're going to see, the sequence that we are going to see will be typical. What does it mean to be typical? Well, about, in this case, fraction of p 1s, fraction of 1 minus p 0s, and therefore a probability which is about 2 to the minus nh. Okay? And the set of all such sequences, how many are there? About 2 to the n h. And it's a really small set, right? Because if you think about the set of all possible sequences, right? So here are, right? So this is just a cartoon, okay? So this is the set of all, let's say again, in this example, binary sequences. So this is all binary sequences. Sequences, right? How many binary sequences are there, like of length n? Right? How many binary sequences? So among all the possible values that this thing can take, right? How many possible values does a binary n-tuple take? Right? 2 to the n, right? All binary sequences. So the size of the set of all binary sequences is 2 to the n. Okay? And in it is a really small, I mean, it's not a baller. I mean, it's, it's a really small subset of the typical sequences. The set of typical sequences, okay, of size, essentially 2 to the nh. Okay, which is, so with all likelihood, the sequence I'm going to be dealing with is going to be in this set, in this typical set, okay, which is a minuscule fraction of all the possible sequences, right? Let's see, like about what's the fraction? Like how big is this set, right? This set, its size is about 2 to the nh, right? Relative to all the possible binary sequences, right? That's what? It's 2 to the minus n times 1 minus h. And this, again, we're now focusing on our binary example here. Okay, so now the entropy, this is the entropy of the source which is generating our data. Right? So this is the entropy of a Bernoulli P random variable. Right? And if P is a biased source, if this is not a half, these are not fair coin flips, but this is some P, right, which is not a half, then what can you tell me about the entropy relative to 1? Is it bigger or smaller? Right, smaller. Among all Bernoulli variables, the one that has largest entropy is Bernoulli half. And that's going to have entropy 1. So anything else which is biased will have entropy less than 1. Right? And so if this is not fair coin flips, which entropy is less than 1, the fraction of the typical sequences that you might actually see with any non-negligible probability is an exponentially small fraction of all the possible sequences. Okay, so this is a very big deal. So this is not drawn to scale. This thing is actually minuscule, exponentially small for large n, or as n becomes bigger and bigger. And this has a really fundamental ramification for compression, because what it means is that I can and should focus all my coding efforts on this typical set. I should think about how do I actually design a compressor under this assumption, this value assumption that with all likelihood, the sequence I'm going to have to represent, to describe to the decoder, is going to be here in this small set. right? So, in fact, who can suggest, based on this observation, who can suggest a coding scheme that's going to get a compressor, okay, that's going to get us close to the entropy? Anyone? If I know that my source, the sequence that I will have to describe, right? Let's say I knew probability 1 that the sequence that I'm going to have to describe is in this set, whose size is 2 to the n h. How many bits of description am I going to need? Right? If I need to describe, right, one possible sequence or one possible element among a set of a certain size, right? Then as we've seen, essentially up to rounding off the number of bits that I need to basically describe or index the possible elements in a set of a certain size is log the size, right? So if I knew that my sequence for sure is in here, right, I would need essentially log the size of the set, which is essentially n times h bits to describe it. But now I know that with all likelihood it's going to be here, and with some negligible probability it's going to be something else. Then how can I use that to construct a maybe variable length code, variable length compressor that will come close to compressing down to essentially the entropy of the source? Anyone want to try?
If it's inside the set, then the compressed string starts with 1, and then there's some sequence of bits that just enumerate the elements of the set, and we know that's n times h bits, and then otherwise it starts with a 0, and then it's just fully compressed.
That sounds like a pretty good idea. So let me try and recap. So what the encoder is going to output is first basically 1 bit to indicate whether the source sequence is typical, right? To indicate whether the sequence is typical or not, right? So I'm going to see my realized source sequence. I'm going to ask, wait, is it in this set or not? I'm going to first give you output 1 bit to tell you whether or not it's typical. If it's typical, right, then after this first bit, I'm going to use essentially nh bits, because I'm going to use essentially log the size of the typical set bits. That's all I need in order to describe one element in this set. Right? To describe it. That's if it's typical, right? So if it was typical, then the decoder knows now that, okay, we're focusing on, you're describing me now just one possibility from here, and I need just log the size of this set to describe it. But if that bit indicated that it's not here, it's maybe somewhere here, then let's just use, right, the n bits. Let's be wasteful. Maybe we can get away with less, but let's say now, okay, so it's just some binary sequence of length n. I don't need more than, so I'm just going to use n bits to describe it if it's not typical. Okay, so, right, so for this scheme, what is the expected length, the expected number of bits that this scheme will require for encoding, for describing the source n tuple xn, right? So it's essentially right, well, it's going to be, okay, 1 bit. It's going to be definitely no more than 1 bit, right? Just 1 bit to indicate whether a sequence is typical or not. And then, right, plus, with all likelihood, with probability essentially 1, then I'm going to need n times h bits. And then, okay, I also need to account into this expectation the really small probability, let's call it epsilon n. Okay? This is the probability that the sequence is not typical. Okay, on that event, I'm going to need, okay, n bits. Okay, and in terms of then, right, on average, expected number of bits per source symbol, right? So I'm normalizing by the number of source symbols that I'm describing. Right? So this is going to be about h, right? So for n, as n grows, this is going to be, again, this is going to be extremely small, right? Because this is the probability of being atypical. And this is vanishing. So with this kind of scheme, we were seeing that we could get arbitrarily close to like achieving the entropy. Right? As we work with larger and larger blocks of data, everybody okay with this? Okay, so this AEP, by the way, why is this called the asymptotic equipartition property? Because of this property that asymptotic, because it's sort of when n is large enough, so kind of the law of large numbers starts kicking in, then essentially what we have is that all the action happens in like this small subset where effectively we have like a uniform distribution on the typical sequences. They each have probability about 2 to the minus nh. And also, in fact, implicit in this AEP is is the fact that we can come close, arbitrarily close, to compressing with no more than essentially h, the source entropy bits per source sequence per component. But it also actually implies, or let me ask you, could we do better? Like potentially, can we do better than H, the entropy? Can we get away with lossless compression with less than H bits per source symbol? And actually, implicit in everything that we just did is the fact that you cannot. Okay, so let's think about this. So can we do better? Okay, so consider, right, any compressor. So you give me a compressor. And let's say that it uses n times r bits. On average, let's say it uses n r bits to describe the source sequence. Okay, so in other words, r bits per source symbol. Okay, so, or let me just say this, that basically any compressor that you give me that uses nr bits, okay, it's going to be able to represent, right, 2 to the nr possible sequences. Right? So now what if R is less than H? Okay, so what if your compressor is using R bits per source symbol when R is less than H, right? Then let's say that this is, right, so if you're only using nr bits, there's only, I don't know, let's denote this as like, basically this is a set of size 2 to the nr corresponding to the different possible sequences that this, like, I don't know, whatever this scheme was, it's using only nr bits, and the decoder is going to see like nr bits, and so what the decoder is going to decode can only be one of 2 to the nr possible sequences. So, there's like this set of possible sequences that the decoder can output, and if R is less than H, then in fact this set is necessarily a very negligible probability, right? Why? Because this part of the set is atypical, right? I mean, this part has about probability 1, this whole part is negligible. Of course, this part is negligible. And then this part, its size is even less than 2 to the nr. 2 to the nr, if r is less than h, is of a negligible size relative to this typical set, where we have essentially a uniform distribution. So I've got essentially a uniform distribution here, and this is a very small, right, in size part of it. So this thing also has a really small probability. So for now, we're not going to get more rigorous than that, but I hope that at least qualitatively, intuitively, you're with me that this set of size 2 to the n r, whatever it might be, whatever your compressor might be trying to do, necessarily, like the probability that it will succeed is the probability that the source sequence falls in some set whose size is 2 to the n r. If r is less than h, it's necessarily a really, really negligible set in terms of its probability. Okay, so okay, so let me just leave it at this compressor cannot be lossless. No way in hell that this is a lossless compressor. Not only is it not lossless with high probability, not only is it, it's with high probability, it's going to screw up. All right, because with high probability, the realized sequence is not going to be in the set of sequences that this compressor knows how to reconstruct. So, right. Is everybody okay with this, at least on a at least on a qualitative level? Why this AEP tells us that we can achieve compression, lossless compression, on average, arbitrarily close to, with rate in terms of bits per source component, arbitrarily close to H, to the source entropy, and that no scheme in the world that tries to operate at a rate less than the entropy can be lossless. Yes?
Just a quick question. So you mentioned how this AAP can get like arbitrarily close to entropy. I was just curious, is this better performance than when we were just, because like when we would do the block code to size n, we could still get the entropy within 1 over n, and here we'll also add the entropy within 1 over n.
Right.
Is this better than that, or are they the same?
That's a great question, and in fact, Shubham is going to very shortly address it with some plots where we've actually realized both this kind of compressor, which we're calling a typical encoder and decoder, or typical compressor. What you're suggesting, it corresponds to, for example, using, right, like Shannon code, right? You're saying, and that's another way of seeing how we can come arbitrarily close to achieving the entropy, right? Like with a Shannon code, right? You're going to take then the length function associated with your n tuple is going to be, right, log 1 over, or let's call it minus, log of 1 over the probability of xn, right? To be precise, this is going to be your code length, right? Which is no more than, within 1 bit of this. And so, right, what's going to be your expected code length if you use the Shannon code right? What is this expectation? Right? What's the expectation of the log of 1 over the probability of something? Right, exactly. So this, in this case, this is the entropy of this something. And if the components are IID, right, then, and I think, did we say this explicitly, or will this be in an exercise, that the sum, that if the entropy of an n-tuple with IID components?
We proved it in
Okay, great, right? So this, you know, is nothing but n times the entropy of each of the individual components, because they have the same distribution and they're independent. And so, absolutely. So here too you see a scheme whose number of bits per source symbol, right, comes arbitrarily close to, 1 over n times hx. So with the Shannon code, you can also come arbitrarily close to achieving the source entropy if you apply it, construct it and apply it on a sufficiently large block of data. And which of them is better? You're going to see some plots very shortly, and you're also going to see that in practice, this is not what we want to be doing to get close to the entropy, because the complexity of these schemes, both in time and in memory, is growing exponentially. We need lookup tables that are growing exponentially, even though it's only, let's say, the size of the typical set with the typical encoder, still, and it's not the set of all sequences, but still it's an exponentially growing set with n. So it's not very realistic when n is large. And we're going to talk about how to actually get arbitrarily close to this thing with very reasonable complexity very shortly. The last thing that I will do, speaking of the of this Shannon code, is briefly talk about mismatched compression. Right? So let's say you knew that your compressor, okay, so let's consider a compressor with a length function. Okay, let's say generically now, it's just like one element. Forget n tuples. Now you've got an element in a set that you want to devise a compressor, a lossless compressor for. And so we know that you can always devise a Shannon code, right? Assuming that it has a distribution. Let's say you assume it has a distribution of probability mass function Q, then we know we can always construct a Shannon code that will have this length function, right? And very precisely with an upper integer value. Okay, but essentially, I mean, what's one bit among friends? Let's just say roughly, up to that 1 bit. If I thought that what I'm compressing is governed by distribution Q, probability mass function Q, then I would try to construct a compressor whose length function is essentially log 1 over Q, right? Because we saw that, if it were distributed Q, then this is going to get me close to the entropy of that thing. But what if, right? So I constructed a compressor that assumes that it's coming from the probability mass function Q, when in fact X, right? In fact, God decided that she wants to generate it according to some other distribution, P. Okay? Then, what's the price I'm going to pay? What's the price that I'm paying for constructing a compressor, assuming it came from distribution Q while it was actually distributed P? Well, let's see what my what the expected number of bits that I'm going to need under this scheme. Well, it's the expectation, right? So, all the possible values for X. It's distributed P, so the expectation is the probability of X times L of X, right? That's probability of X log, right? Up to, so this is log 1 over Q, right? You will allow me to, let's say, inside the log, multiply by 1. Right? So what am I going to get? Sum over the possible values of X, Px log 1 over Px plus the sum over X, Px log, what do I still owe you? So I've got log 1 over P is here. So now what remains is P over Q. Log of P over Q. Okay, so what's this guy? Look familiar? Right, exactly. This is the entropy of X. And this guy, sum over the possible values of X, Px log Px over Qx, is what's known. In fact, we have a notation for it. We denote it. It's denoted.
We also defined it as part of the proof for optimum, the lower bound proof.
Oh, okay, great. So what is this guy? What is this? Right. This is the relative entropy or Kullback-Leibler divergence between P and Q. So we're seeing that, obviously, we already know you can't do better than the entropy, right? But what we're seeing it here is that this relative entropy between P and Q is the price of mismatch. It's the price in terms of excess number of bits that you're going to have to pay for compressing something that came from distribution P when you designed a compressor that assumes it came from distribution Q. Okay? And so obviously, you can never do better than the entropy. And if you assumed, and if you did something, assumed a different distribution, you're obviously going to pay. So this thing is always non-negative. And in fact, it's going to be positive growing, the more, the more different Q is from P. I think I'm going to leave it at that and let Shubham now show you some really interesting plots.
Hi everyone. Thank you, Tsachy, for the lecture. So, as Tsachy said, we will now look at some real experimental results for some of the coders we have seen so far, and depending on time, a few things to wrap up on Huffman coding. So again, with SCL, we basically implemented the typical set coder. You can find it in, we'll provide a link. So basically the same logic, like if you look at some of the functions, you will see there is a function called isTypical, which just checks if a particular sequence is typical. There is a function called generate typical set coder lookup tables, which goes through all the n tuples. For each of them, checks if it is typical and enumerates them as the coding scheme suggested, basically. And then the actual coding you can see here. So here, line 114, if chunk to encode is typical, then you put a 0 followed by the encoding within the typical set. Otherwise, you put a 1 followed by the encoding in the entire set, right? So take a look at home. It's a bit slow, as you can expect, right? Whenever you have exponential complexity, right? Like blocks of 10 work fine, 20 it takes like several minutes, 30 it will never finish. So we ran it until 10. Okay, so what we did was we set up we will share this notebook. Notebooks are very hard to scroll for some reason on this. We'll see. Okay. Yeah, let's just look at the results. I think this will. Okay, so what we did was we have here 3 coders. We have the Huffman code, we have the Shannon code, and we have this typical set code that you just learnt about. There is a parameter here when you go into the details to, like, what do we mean by approximately equal, basically. So we chose a reasonable parameter for this block size. So for the Bernoulli 0.01 source, we show the red dotted line at the bottom that shows the entropy. So that's basically the best you can ever do. And the purple dotted line, that is the hx plus 1 by n bound that you just saw here, right? So that bound is for Shannon code, also applies to Huffman codes. So you see here that all 3 codes do pretty well, like they're very close to each other. Huffman codes are the best because we know that they are the optimal codes, right? So they are at the bottom, and then typical and Shannon, there is sort of a, depending on the block size, one or the other does better. So this is good, right? The things we saw there, it's gradually getting close to entropy. It's not quite there at a block size of 10, but it will get there because we have that bound, right? Hx plus 1 by n. So we know that at block size 20, you will get within 0.05 of entropy, and eventually you will get very, very close. So all 3 codes have exponential complexity when just for constructing the code book, because the typical set code you enumerate over all the sequences, find the typical ones. That's exponential complexity. Shannon code, again you have to go through every sequence. Just building that tree is exponential complexity for all 3 of them, and then storing that tree or storing the code book in your memory, that's also exponential. So we also plot below. This shows the time for code generation, so generating the code book or the tree versus block size for the same source. Huffman is really like dominating all of this. I wouldn't worry too much about their relative scaling because that also depends on our implementation. Huffman code is just doing a lot of work with that particular algorithm to merge things and so on. So to maybe make it easier to see, here I put the time on a log scale. So a linear growth on a log scale is exponential growth in the like in the normal thing. So you see all three are going basically linearly on this scale. So all three are exponential. None of them is going to scale very well, right? And if you want to use these codes, basically what will happen is you will need to restrict yourself to some smallish block length, and you will deprive yourself of like actually achieving entropy. So that's just not ideal situation. So what you will learn in the next 2 lectures is a way to achieve entropy, effectively have very big block sizes without having this exponential complexity. So that will be the focus of the next week. This was, I think, for a bit now, this will be the last theoretical lecture. After this, it's mostly algorithms for the next 5 lectures or so. Okay, any questions on any of these plots? Okay. Right, and we'll provide a link to this notebook and the typical set coder code on the website. Okay, we have some time. Let me wrap up a few things I wanted to do in the last lecture. I won't recap. I think it should be pretty fresh in your minds. Ask me if you have any doubts, right? So as you remember, right, we talked about Huffman codes and talked about the tree construction. We talked about how it was the optimal code. We looked at some examples on some real life data. We also talked about this table-based decoding, which is a faster way of decoding Huffman codes, which you will also see in your homework. One thing we didn't get to was, where is Huffman code used? So it's used in a lot of very common algorithms, some of them which you use almost every day, like JPEG in particular uses Huffman coding as its last stage. All of these do a lot of things, but at the end of the day, when you have some stream that you want to entropy code, you use Huffman coding in these ones. So let's just look at one of them. Let's look at deflate, which I already opened up. So this is a RFC which like describes the entire format for deflate. If you have already looked at question 5 in your homework, that talks about like if you have a Huffman code, you need to, when you send it to the decoder, how will the decoder know what Huffman code is the encoder using, right? So there should be a way to either you send the probability distribution over or you send the Huffman code over, but there is a third possibility. The third possibility is shown in section 3.2.6, which is compression with fixed Huffman codes. So in many cases, the gzip files, they just have a hard-coded Huffman code in them. They just looked at a lot of data, found a reasonable distribution, and it just uses that standard Huffman code. Both the encoder and the decoder have that in there. Basically, it's part of the format itself. So in a lot of practical applications, you will see that you don't like try to learn the Huffman tree on the fly. You just use a standard Huffman tree, which you learned like basically designed beforehand. It's like a hyperparameter sort of thing where you just fix it beforehand. Then you could also have a dynamic Huffman code. So both are supported in the format, right? So now the question comes like, how do you represent the dynamic Huffman code? How do you transmit it to the decoder side? So in the homework problem, what you are doing is you are encoding the probability distribution, sending it over, and then the decoder decodes the probability distribution and builds the Huffman tree on the decoder side. Gzip does not do that. And the main reason is like, if you look at the Gzip, I encourage you like, maybe not now, maybe after lecture 10, read this entire RFC, which describes the Gzip format. And you will see how like for each and every bit, they like think like twice, like how can I avoid spending this one bit while being super fast. So it's very interesting. So that's right. This is from the JPEG format where again you have some fixed Huffman codes in there. But what I want to talk about is an alternate way of transmitting your Huffman code to the decoder. Not the thing you will do in your homework. This is different and not what you will do in the, yeah. So this is like, I just drew a Huffman code. This is some Huffman code. Don't worry about the distribution. Some Huffman code. Okay. There are a couple properties here. I guess let me draw another Huffman code here. So you have this Huffman code. Maybe you can have another Huffman code where you just like reorder the symbols a bit. You do like, you still put A here. And then maybe you can like reorder C and D. And then you can put B here. This is like basically equivalent Huffman code to the one on the left. And it will get you the same expected code length and everything, right? So Huffman codes are not unique. When you're breaking ties, when you're building the tree, you have some flexibility. And then when you're putting which one to put on left, which one to put on right, there is some flexibility. So just generally you will see that the algorithm is not like fully deterministic. There are multiple Huffman codes corresponding to the same distribution. So that's what makes like transmitting it so hard. Like, I don't know if you started on question 5. Last year, lots of people have had issues because they were just like, you just need to be careful that you do the exact same thing on the encoder and the decoder. Otherwise, the whole thing breaks down. So there are like a couple of properties that you have in the left code, which is one is that there are longer code words to the left and a shorter code word to the right. Okay. Sure. And then there is another property that you have C and D, and C comes like lexicographically before D, right? It's alphabetically smaller, but it's to the right of D. So this code, according to the definition of canonical codes, is not canonical. Canonical codes have a few properties. They are sorted by code word length. So anything on the left should be shorter than anything on the right. So as you go from left to right, your thing should grow. And if you have two code words of the same length, the one on the left should be the lexicographically smaller. So C should come before D. A should come before B if A and B have the same length. Right. So what you can show, you can reason about it, like basically you can just like shift around the tree, and you can show that for any Huffman code, you can convert it into a canonical code, which has these two properties basically. That it's sorted by code word length from left to right, and for the same length, it's sorted lexicographically. Any questions on this? Let's do one example where what I will try to show is, for a canonical Huffman code, you don't need to send the probabilities, you don't need to send the structure of the tree, nothing. You just need to send the length of the code words, and that is enough to reconstruct the code book basically. So let's try to do this. So you start with the smallest one. So this is the one you start with, b equal to 1, right? And you know that this has to be to the left of every other code word. So first thing you do is, you know that this b has to be on the left of everything. Okay. Which is the next one I should pick? A. Can anybody tell what is the code word for A? Yeah, it has to be 1, 0, right? Because we know that we are always going left to right. So this is the only possibility basically. So A, right. Now, I have both C and D which are length 3. So which one should go on the left and which one should go on the right? Yeah, C has to be on the left again because of the property of canonical codes, right? So if you have a canonical code, you just need the lengths of the code words to be able to reconstruct the entire code, right? So it's a very, very efficient representation as opposed to like storing probabilities. Also like cheap to reconstruct on the decoder side. Like it's a very simple algorithm to get back to the code book. Any questions on this? Okay. So gzip uses canonical Huffman codes, right? When they are using this dynamic coding strategy. Can anybody suggest how you would store these lengths? Any ideas on how you would actually, because you need to transmit the lengths you need to put the lengths in the compressed file. How would you store the lengths? Any ideas? For example, let's say I know that the lengths are at most 16, or the lengths are at most 8, So how could you represent the lengths? It's not a trick. It's a simple question from what you have learned. So you know the lengths have to be a prefix-free code, right? So that the other side can reconstruct it, right? So one simple thing you could do is you just store with, let's say if the maximum length is 8, you just do like 3 bits per length, right? And you have however many lengths, you just transmit that way. Obviously gzip, as I said, right? Gzip is very, very concerned about being very efficient. Yep. So what gzip does is, the Huffman codes for the 2 alphabets appear in the block immediately after the header, whatever. Each code is defined by a sequence of code lengths using the canonical description. For even greater compactness, the code length sequences themselves are compressed using a Huffman code, right? So you compress your data with Huffman code, and then to describe the Huffman code, you store that with another Huffman code. So you will see like how much they're like concerned about the space. And the way gzip does it is it uses a static Huffman code for storing the lengths. So like in gzip, what happens is, so you have the whatever stream, so that's stored with a dynamic Huffman code, right? And then you need to store the lengths of this thing, which are stored with a static Huffman code. So it's a Huffman code whose table is fixed basically. So just like, there are like different ways people use these things, but in gzip, like this is how it's done. Any questions? Okay. Okay, in the remaining time, let's go over the quiz quickly. Okay, and I hope most of these you will be able to help me out with. So we had a question 1. We asked you to construct the Huffman code for Bernoulli 0.5. Anybody? Yeah, just like it's a simple code, right? Not much you can do for just 2 symbols. Bernoulli 0.9. Yeah, it's the same thing. Okay, good. Okay, 1.3. How many think it's true? Okay, a lot of people think it's true. And it is true, right? You know, why is it true?
Because like whoever add the entropy, because it's like 0.5.
Yeah. So true because entropy is 1 in this case, right? And so you can't do better. How about 1.4? I see some heads shaking. So the answer is false because entropy is less than 1. How do you square this with the fact that Huffman codes are supposed to be optimal?
We can do like block codes that get better.
Yeah, so I'm hearing that we can do block codes, which is true, right? Yeah. If you are forced to do just one symbol at a time, then this is indeed optimal. But we didn't say that you are forced to do that here. So if you assume that and then you wrote the answer, I guess talk to us, we'll see. But yeah, so basically you can do block codes here. And we saw, right? We saw in that example how it was like dropping with the block size. Okay, any questions on this? Okay, let's move on. Then we have the second question where you had an alphabet with 4 symbols and uniform distribution over the 4. So the Huffman code, as you know, for a uniform distribution, it will be a fixed length code for a uniform distribution over like four symbols. So we have the Huffman code here. And then there was this other code that it's a prefix-free code, right? No particular properties as yet. And then we said you have a particular sequence, A, B, 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 C, D, right? So first part was like the encoded length with Gandhi code, and you can actually do the encoding 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. So I'm getting 15. I hope that's correct. Okay. And then for Huffman code, you have 8 symbols, 2, so 16, right? So we see that in this particular case, Huffman code was beaten by Gandhi code. So question 2.1. Gandhi codes are optimal for this source. How many think it's true? How many think it's false? Okay. But we saw, right? We saw that you beat it. Like, yeah. So I guess the last part gives you a hint in a way, right? But, oh, sorry, this should be 2.3, 2.4, okay. So this is important to understand, right? Like you have a source. A source is a probabilistic source. And when we say it's optimal, what we mean is that the expected length cannot be better than the entropy, or Huffman codes gives you the minimum expected length. We don't say that for each and every particular sequence realization, Huffman codes are going to be better. That's just not possible. You can't have a code that's better than every other code on every possible sequence. Because in particular, what you could do is, like, if you want to only transmit one particular sequence, what you would do is, and if you're allowed to use block codes, what you could do is for that sequence, you define the code as 0. And for the other ones, you then define whatever, right? So if you know, like, you have to transmit this particular sequence, you can always cheat. But the whole game is about, like, transmitting something useful. And it's useful only if there is uncertainty. So that's why we work in the probabilistic setting where the decoder doesn't already know what you're going to transmit. Right, this happens a lot in compression where there are these compression challenges where, like, you're given a file and you really want to compress it to be as small as possible, right? So what I could do is I could create a compressor-decompressor pair where the compressor just sends nothing, or it just sends like 1 byte, and the decompressor has the entire file as part of the decompressor. So the decompressor just gets that 1 byte and expands it out to the entire file. So that's like a way of cheating in a way. So that's why, like, these compression challenges also have, like, you can't have a decompressor that's too big. Right? So the whole thing is, like, the decoder shouldn't already know what is going to be transmitted. Otherwise the decoder, like, what's the point? Why are we even sending anything? So for this particular instance of the source, you can actually show that, like, if you look at the distribution here, so A occurs 3 out of 8 times, B occurs 3 out of 8 times, C is 1 over 8, D is 1 over 8. And if you use this and you construct the Huffman code, you will see that the Huffman code is this one, right? So this is the Huffman code for this distribution, and hence it is actually optimal for this thing, right? So yeah, it's important, like, for particular instances, you can do things which are different from the overall optimal source. And when we say optimal, we mean in expectation, right? So this is already done today. Theoretical interaction between entropy, block coding. And as I said, next lecture we'll talk about practical codes, which will be useful not only to get closer to entropy, but also very crucial for adaptive schemes, non-ID source compression, places where you don't want to assume you know the distribution already. Just a lot of exciting stuff coming up. Thank you.